So equation 7 talks about diffusion equation on P side, which is given as delta NP. This equation you need to remember, and this last equation, the result and these two things. There are two different ways you can write this equation. So these two different forms you need to remember here. So delta NP e to the power of minus xp by ln. Okay, so this is the equation which you need to remember. Last we defined about this each of these parameters here. Okay, next is diffusion equation on n side, which is given by delta of p of xn, which is equal to this delta pn times e power minus xn by lp. This equation in two different forms you need to remember. Okay, now let us consider equation 8 to derive the diode current equation. So equation 8 is this is delta of p of xn, which is equal to delta pn of e power minus xn by lp. Considering now whole diffusion current density, so Jp, this is again we have discussed in module 1. I need not again stress this equation. So this is whole current diffusion. J means it is a current density. P stands for whole here. So this is diffusion. Okay, whole current diffusion. Okay, density is given by minus q times dp and dp of x by dx. Now we know that dp p of x, which is already given from taken from equation 8 here. So the same equation you can differentiate here, and let us see what equation resulting equation what we get. So minus q times dp into d of we have rewritten as it is this equation 8 here. Okay, so this is equation 8, and dp can be taken out. This is from out, and you can differentiate this, which again results in same equation with minus 1 over lp. So this is after differentiation what you are seeing. So you can say this is my differentiation of this equals minus 1 over x 1 over lp into e to the power of minus xn by lp. So this is differentiation term here, and this delta pn last we showed about this equation 5, which you can use that equation 5 if you can recall. Here we have equation 5, delta pn equals this equation. You can substitute over there to obtain overall diode equation. So this is after substituting this for pn from equation 5, you get all these terms, this minus and this minus cancels each other, and you can separate out terms here. Q dp by lp, you can put it in the first, that is a constant parameter, and there is a pn. Okay, so this is holes on n side, which is determined by the doping, and there is an exponential term here, e power qv by kt minus 1. This is also determined by the applied voltage. There is a v here. Rest all terms are going to be constant. Q, K, T are all constants. So only thing is v is the variable here. Okay, this complete term is determined by the voltage what we applied, and direction of voltage that we have applied, and last term is also a constant, e power minus xn by ln here. So xn represents a distance on the n side, and lp is nothing but diffusion length for holes on the n side here. Okay, so these are the various terms which you need to understand. So far we derived the diode current equation. After segregating, you can see that this can be written as final equation. So this is the final equation after separating out. Okay, so equation 9 that we are calling here. So now you can see that at xn is equal to 0. So at xn is equal to 0 means it is at the junction. Okay, so you can see here, this is the PN junction we have shown here. This is the point where at xn is equal to 0. So this is a neutral n region. This is neutral n region. Okay, and here this is the edge of a depletion region what you are seeing here. Okay, this is edge of a depletion region. So at this particular point, the whole current density due to the diffusion at xn is equal to 0 can be calculated by substituting xn as 0 here. So this term will get eliminated, and you have left out with only the first term. This terms, first term here, if I put a bracket here, and this second term here, except this will get eliminated because of xn is equal to 0. So whole current diffusion density is this. Okay, q times dp by lp into pn into e to the power of qv by kt minus 1. You can call this as equation 10. Similarly, you can also write electron current density due to the diffusion. Okay, on similar lines, you need not derive it, but wherever there is a dp, the dn will come. You can also see simultaneously this two equations. So here you can see the dp has become now dn here, lp has become here ln, and pn has become now np. So with that changes, you can write whole current electron current density has jn of diffusion at xp is equal to 0. So this distance is xp. Here you can see we are pointing out from the edge of a depletion region towards neutral p region. This is an xp. To make, if you make it xp as a 0, you will be at the edge of a depletion region here. Okay. Similarly, earlier we have discussed, when you make xn is equal to 0, you will end up here at the edge of depletion region to the n side. This is n side, and this is going to be the p side. Similarly, if you make the depletion region as if you want to arrive at the depletion region, you need to make xp as 0. So if you do that, you will get resultant equation as this. Okay. So now we have arrived at electron current density, diffusion current density, whole diffusion current density. Now together you can add up together so that you obtain total current flowing through the diode. So total electron and hole diffusion current density is given by, so this is the equation, which is a lengthy equation. Including all the process, you can write the total current density J total as we can call as a J here, which is equal to Jp diffusion hole current density, diffusion electron current density, drift hole current density, and again drift electron current density. So in under the forward bias condition, you know that there is no drift process, so this gets eliminated, and though those quantities are going to be very small under the forward bias, so these quantities can be neglected here. So therefore this becomes 0 during forward bias, and hence the drift currents are neglected here. You can neglect those drift currents, and these two becomes majority currents here. So whole current density due to the diffusion process, electron current density due to the diffusion process. So now whatever we derived from equation 10 and equation 11, that can be substituted here for this equation, and you can obtain final diode current equation here. Okay. So if you arrange substitute together, for Jp diffusion and Jn diffusion, these are the equation what you get it here. You can see this is a lengthy equation here. You have different constants on electron current density and hole current density. The one common thing what you can observe in both terms is e to the power of qv by kt minus 1. So we have this term here and we have this term here. This can be taken as a common factor. So if you take out this e power qv by kt minus 1 as a common factor here, you can arrange other terms, then you get this final equation here, q dp by lp into pn. So this is going to be the on the p side. So this is dn by ln into np. Okay. So electrons on the p side, this is actually for the p side. Okay. So this is for the n side. Okay. So these are holes on the n side here. Okay. So this represents n side, this represents p side, and that's multiplied with e power qv by kt. Okay. So now let us arrange terms and call by suitable name called as a saturation current here. So now current diode current is the thing, but the current density into area, this is the definition of current density, or current, other way you can say that current density J equals current by area. Okay. So this can be cross multiplied, so you get the current as J into A. So that's what we have shown here. Current equals current density times the area, then area gets multiplied with the Q, so that you have dp by lp into pn plus dn by ln into np. So this whole terms can be separated out, and that can be called as saturation current. Now we have a mathematical equation for this saturation current. So I naught equals this whole term you can indicate for I naught. And there is a voltage dependent term, last term, which is an exponential term e power qv by kt, and here v depends on plus Vf or minus Vr, depending on the type of bias, forward and reverse bias here. Okay. So the final equation what you see in many textbooks is this: I is equal to I naught into e power q v by kt minus 1, where I naught is given by this equation. Okay, this is reverse saturation current equation. Okay, so you need to remember this, I naught equation, so that whenever it is asked, you can easily substitute the values for this dp lp. dp is diffusion constant for holes, lp is the diffusion length. Last class we defined it, this is how much distance, okay, the holes can travel deeper in the n side before it get recombine with the electron here. So Pn indicates the holes on the n side. This is minority carriers on the n side, because I naught is nothing but it's a reverse saturation current, so it depends on the minority carriers. So Pn means it is holes on the n side, and Np means it is electrons on the p side here. Dn is diffusion constant for electrons, and Ln is nothing but it is a diffusion length for electron. So how long the electrons can travel deeper in the p region before it get recombined with the holes on the p side. Okay, so this is what equation tells you, and look at this I naught, and we will analyze on what parameters this reverse saturation current depends upon. And if you observe this I naught equation, the various terms that are associated is as follows: q, which is a charge of electron, that is not under our control, so it is not controllable. But area of the PN junction, that matters a lot. Area of depletion region, that matters a lot here. So by varying this area we can control the reverse saturation current, but to some extent, not to a larger extent. And if you look at dp here, this can be written as kt by q, and again it is a factor, it is related with the mobility. So mobility is interrelated to the doping. Of course, this also can be controlled by this dp can be controlled. That means via the doping, if you increase doping or decrease doping, you can control the mobility here. And we already showed graph about this doping and the mobility with reference to different materials in module 1, just to go through that. So via this mobility you can also control this, the diffusion constant for holes. And LP is nothing but called as a carrier lifetime. It depends on how long the hole can travel deeper in the n side before it get recombined here. So this is the length it measures, to what distance it has traveled, LP. Okay, so even this also varying this LP, the more distance it travels, that also the current reverse saturation current also keep varying here. So this also the I naught can be varies depending on the LP, diffusion length for holes. And lastly we have the Pn, the parameter Pn. There is nothing but holes on n side. So this depends on the amount of the doping. Okay, so this varying the doping, if you decrease the doping, that can cause the change in the reverse saturation current here. Okay. Okay, so equation 12 is the diode current equation in the forward bias. We can calculate diode current equation for the reverse bias also by substituting V is equal to minus VR. So this is the relation which you can substitute for reverse bias condition, so that you can obtain diode current equation for the reverse bias. So the same thing we have done here. So you can see the other terms we have kept constant. Okay, the first few terms you can observe here we have not at all changed here, only change is here this. In place of V we have minus VR, and you know that when VR is it's a negative voltage, and if it is a very large, this exponential term becomes very small. So this if it is larger than the KT by Q, so then the whole exponential term becomes the negligible. So you can remove this, and so you get the equation for reverse saturation current. So then I is equal to, now we can see after substituting this as a 0, we have this equation: I is equal to QA into dP by LP Pn plus dN by Ln into Np into 0 minus 1. This you can simplify this, you will have a negative sign here. So I is equal to this, this if you observe it entire term here, this is now equivalent to I naught here. Okay, so this is now reverse saturation current I flowing in the reverse direction is equal to minus I naught here. Until the breakdown occurs, this I naught will keep on flowing through the PN junction here. Okay. Okay, I think we have shown so far the diode current equation both in forward bias and reverse bias. Any questions or any doubts you have? before we move on to the reverse bias. Okay, if you don't have a doubt, let us proceed to the reverse bias. Reverse bias, so far, we have discussed current equations, the that are flowing in the diode. Now let us start looking into the particularly to the reverse bias here. In our earlier derivations of carrier injection, so far we have seen carrier injection, minority carrier injection, majority carrier injection, flowing due to the diffusion process and due to the drift process, the minority carrier distributions, everything we have seen with reference to p-n junction. And there we have assumed initially the forward bias, and later on you can also calculate equations relevant to that based on reverse bias also. So, the distributions for reverse bias can be obtained from the same equations if a negative value of voltage applied voltage V is introduced. Last class we deduced, we obtained the equation for a general voltage V, and now we need to transform this equation for the reverse bias here. In the equation what we have obtained for the general, the voltage applied voltage V, you can change that to reverse bias by modifying that V as minus VR. You can see this, if you change V is equal to minus VR. So, the P region now it becomes negatively biased with respect to the N region, and then equation 5, okay, so recall the equation 5 and let me take you to the equation 5. Okay, so you don't forget, where we have, what is that equation 5. This is the equation 5, and you can observe here we have only term is V. Okay, so we mentioned in the last class V becomes Vf for forward bias and V equals minus Vr for reverse bias. Okay, so though we have given here general equation, this can be changed according to the forward and reverse bias. Okay, this is delta Pn. So change in the holes concentration, hole density on the N side. So this is again excess electron concentration on the p side. This indicates minority carriers, of course. Both equation 5 and 6 represents minority carriers. Now let us move to the derivations, derivation part under the reverse bias here. Okay, the rewriting same equation, we can approximate that equation now. Delta Pn now becomes equal to, we will see what approximation we can do here. So, delta Pn represents excess hole concentration, okay, on the N side. So, they represent minority carriers, which is equal to Pn into e to the power of q minus Vr we have here by Kt minus 1 as it is. So, this is the condition of the P-N junction under reverse bias. You can see that P is connected to the negative and positive terminal of battery is connected to the N region here. So, this is a reverse biased P-N junction. Now, in this equation you can approximate that Vr is going to be very large compared to the Kt by Q. You can see that this is a Kt by Q, which is in the denominator term. If you transfer this, if you remove here this, if you make it this as Kt by Q, and you can see that if Vr becomes very large compared to Kt by Q, since Vr is going to be a negative, so that this entire term will becomes the negligible, and you will have excess hole concentration on the N side, which is equal to approximately equal to Pn times 0 minus 1. So, this minus 1 is again kept as it is. So, this becomes minus Pn. So, finally, we have derived this, let us call this as equation 15. So, delta Pn, which is nothing but excess hole concentration. So, this is excess hole concentration, okay, hole concentration, okay, on N side, is given by this equation. Okay, so this represents minority carriers here. Similar equation can be obtained for excess electron concentration, that is equation 6 if you consider, and if you can approximate same what we have done here, you can obtain equation for delta Np also. So, delta Np is nothing but approximately equal to minus Np here. So, you can see here delta Pn is equal to minus Pn, delta Np is equal to minus Np here. So, let us call this as equation 16 here. Now, let us see what this equation 15 and 16 represents here. From equations 15 and 16, it is clear that for a reverse bias of more than few tenths of volts, the minority carrier concentration at the edge of a transition region becomes essentially 0. Okay, as the excess concentration approaches the negative of the equilibrium concentration. So that means we start with the negative, and as you go towards the edge of a depletion region, it becomes 0. Last class, if you can recollect, we have showed this curve here. You can see that this is the minority carrier distribution under reverse bias. Okay, so whatever we talked here about delta Pn, this equation here, this is delta Pn, you can see in this here. Okay, so this is a delta Pn which decreases as you move towards equilibrium or edge of a depletion region here. Okay, it becomes closely, it becomes 0. Okay, similarly on the P side, you can show that this delta Np also, you can see that delta Np. So this is how the exponential relation what it is showing here. So all these equations also shown in this slide for your reference. Okay, so that shows the excess concentration of on both P side and N side here. So the excess minority carrier concentration in neutral regions are still given by equation 7 and 8, but they are the actual equations. So that can be the approximated here in the as we have shown here. Okay, by when we go for reverse voltage. And here we have a different graphs which will tell you about this, the PN junction under reverse bias. This is PN junction under reverse bias. Type of PN junction what we have preferred is P plus N, and this is a distance from the mid of a junction. Xn naught is edge of depletion region on N side, minus Xp naught is edge of depletion region on P side. And this graph below that, what you can see here is under reverse bias condition. Okay, so under reverse bias condition, this graph is now which is equal to delta Pn, which is approximately equal to minus Pn. So this is negative of equilibrium concentration. That's what this excess hole concentration on N side shows. And this curve approaches the equilibrium as you move deeper into the neutral N region here. So this is how the curve moves. Okay, so when you go deeper into the N region here. So you can see this y-axis here represents the P of x, and this is hole concentration on the as a function of distance versus the distance in the neutral N region, which is nothing but xn. Similarly, if you plot a graph of electron concentration n of xp, okay, this is electrons on the p side as a function of distance xp here. Xp is nothing but distance starts from minus xp naught. Here this xp is 0. Okay, at this point. Okay, at this point this xp is 0, and xp keeps increasing as you move deeper into the neutral p region. And similar thing also applies for N side. So here at this particular point xn is 0, xn is 0, and as you move deeper in the neutral N region, xn keeps increasing. So this is xn. Okay, so this when you move deeper into the N region here. So now if you plot the carrier electron distribution and the reverse bias here, so if you can see here, this is electron distribution in the p region. It starts the approaching the equilibrium region. So this is equilibrium. This line here NP represents equilibrium. This straight line represents equilibrium here. Okay, so this approaches equilibrium. So this is equilibrium, this point. Okay, so this is equilibrium. Okay, so which is nothing but NP. So as you move deeper into the N side, the electrons level, because electrons will tend to diffuse with the holes which are present here, and that diffusion process will just end up when you move deeper into the p side here. Same thing happens here also. So as electron keep moving, holes here in this case, holes keeps moving deeper into the N side, they get the recombine with the electrons here, and they tend to become approach the equilibrium condition here. Okay. Okay, so with that, let us see the second graph shows the variation of quasi Fermi levels. The quasi Fermi levels you can see under the reverse bias condition. So this is EFN, which is much below this EFP. Under forward bias, you have already seen that EFN was at higher potential, higher energy level compared to EFP. But due to the reverse bias, now, so this EFN, okay, what you are seeing is this is called the quasi Fermi levels, that is much below this EFP. Okay, this is a Fermi level as you are seeing here, and the exact Fermi level, and to what extent it has been decreased, it is shown as EFN. So, same way here also this is Fermi level, actual Fermi level, and you can see that on p side EFP is higher level. Okay, this is what it shows you in the, this is energy band diagram, under the reverse biased PN junction. Okay, so this is the amount of the potential, barrier potential that is existing in the PN junction here, and you can see that the holes, minority carriers on the n side, they causes the, because of strong electric field here, that causes drift of holes from n side to the p side, and the electrons keep drifting from p side to the n side because of the electric field that exists in the middle of a junction. Okay, so these are the various graphs which you need to aware of here. So in this observation here is under the reverse bias conditions, this EFN is going to be lower than the EFP. Okay, so EFN represents Fermi level on the n side, EFP represents Fermi level on the p side. The same thing has been explained here, which you can go through this instead of covering each and every point here. So this is what I said here. Fn moves the away from the EC, and FP moves away from the EV. So those things has been showed in the graph here, you can see here. Okay, so Fn and Fp, they are far away from each other, you can, when you see here. Okay, so that's what it is told here. Fp moves away from the EC, not Fn. EC is nothing but conduction band level here. You can see that this is EC. Okay, so this is EC, so it keeps moving away from the EC here. Okay. Okay, so with that said, in reverse bias, the depletion region, we can also take product of this NP or PN, that gives you Ni square into e to the power of Fn minus Fp by Kt, that is approximately equal to 0 in the under reverse bias condition. Here we have reverse characteristics. We have under the forward bias, which you can see here, this is the forward voltage. Once it threshold exceeds here, the current exponential current keeps flowing here, and under reverse bias, even though we have merged this line with on the x-axis here, there is small amount of reverse saturation, very small reverse saturation current flows here, and till breakdown, that small amount of reverse saturation current flows. Once breakdown happens, you will have a large surge of the reverse breakdown current here. Okay, once it exceeds this VBR here. So this is the diode circuit under the forward bias condition, where we have connected P to the positive, N to the negative, and this is the current limiting resistor. What you are seeing here, current is flowing from P to N region in the forward bias. When you apply reverse bias, to apply reverse bias, this is the circuit setup here. What you are seeing, P is connected to the negative terminal of battery, N is connected to the positive terminal of battery. This is again current limiting resistor, which is in series with the PN junction. Using these two circuit, circuits, you can obtain this voltage current characteristics here. Okay. So we will talk more about this. We can also approximate. If you observe overall this characteristics, it is non-linear in nature, because you can see that exponential current flows in forward bias, and the very small amount of current flows in the reverse bias until breakdown occurs, and huge current surges when the diode breaks down here. Okay, overall this characteristics is non-linear, but several the models have been developed for the PN junction to show it is an this also can be used as a linear model. So we will see that one by one. Okay, the maximum reverse current which can flow in a device is E minus VBR. VBR is nothing but the breakdown voltage, E is nothing but applied voltage. If you take difference of this by R, that gives you the maximum reverse current flows through the device. Now again, if you look at breakdown mechanisms, there are two different breakdown mechanisms. One is that explanation can be given in two different ways. One is Zener breakdown, and the other one is avalanche breakdown. Now let me move to the presentation slide before we take up this problem and explain these two breakdown mechanisms here. Okay. So this all things has been shown here, and this is what Zener breakdown. These currents will discuss in the coming classes soon. Okay. Okay, look at this Zener breakdown. So Zener breakdown occur when there is a high reverse bias and a heavily doped PN junction. These are the two conditions for the Zener breakdown to occur. First condition is there must be high reverse voltage, and when there is a high reverse voltage and if the diode is heavily doped, so definitely the Zener breakdown occurs here. In this case, what happens, let us see here. So, the electron from the valence band, it will tunnel to the conduction band on the n side. So, tunneling is one of the important phenomenon that occurs in the Zener breakdown. So, tunneling can occur if the EVP, valence band energy level, and ECN cross each other, as you are seeing in this diagram here. So, this is conduction band energy level and this is valence band energy level. They are in this case, first at equilibrium condition, you can observe here they are far away from each other, but whereas in reverse bias condition, so EC conduction band is below this valence band on the p side here. So, under this condition, definitely tunneling of electron will take place here. Okay. And also we can observe that width has become very, the width of the depletion region is very small because of the uh, uh, this to conduction band is very low than the valence band. So, now this under this condition the Zener breakdown typically occurs under heavily doped junction at few volts of reverse bias. In the sense, few volts means usually the breakdown may occur at the -5 or -6, -7. So, volts, -7 volts. So, that kind of breakdown is called Zener breakdown here. Okay. And here we have an energy diagram, energy band interpretation of the Zener breakdown. As you can see, there are two bands here, conduction band on both p side and n side. There is a valence band here on both p side and n side. And this is nothing but the electrons which you can see here. This is the shaded portion here indicates an electron here. Okay. This is under equilibrium. But when we apply reverse bias, you can see that the barrier potential keeps increasing and the conduction band energy levels keep moving down, and there is a split up in the Fermi level, as you can see here. On p side there is a Fermi level which is above, on n side the Fermi level is below here. Conduction band energy level crossed this valence band energy level. Now, electron which is present here, okay. So, you can also see here all these the states are completely filled. There is no empty state in the valence band. So, in such a scenario, the electrons sees empty positions, empty. There are a lot of empty states in the conduction band. So, electrons they see, whenever they see, observe it, there are completely states are filled here and there is an empty state here, and when sufficient negative voltage is applied, electron will hop into this conduction band here. This process is called as tunneling. So, electron finds the equal the energy state, and there is empty position here when all these positions in the valence band are filled. So, electron keeps hop into, in single hop electron will jump into the this conduction band where there are a lot of empty states here. Okay. So, this process is called as the tunneling here, and more electrons will keep jumping, it will hopping here to the conduction band, and via this mechanism called as the tunneling, and that results in Zener breakdown. And there, as I told you already, there are two breakdowns. One, what we are discussing is Zener breakdown. This occurs at low voltage, and other breakdown, avalanche breakdown, which occurs at higher voltages. Okay. If you compare Zener breakdown and avalanche breakdown, Zener breakdown occurs at earlier than the avalanche breakdown. Okay. I already told you about this. Because of a strong electric field in the depletion region, this hopping of electron will takes place from conduction valence band to this conduction band here, and this process is called the tunneling here. Now, let us we have seen here two different interpretation here. One is energy band interpretation, that is what we have discussed so far at equilibrium condition, and we have compared that with the reverse bias condition. And here we already told about how electron will hop to the conduction band, and due to the strong electric field in the reverse bias region here. So, this more and more electrons, when they keep hopping, this creates the breakdown mechanism, and that is named as Zener breakdown. And let us see this physical interpretation of this Zener breakdown. With high doping, large reverse bias. Okay, in the reverse bias, you know that that we are going to apply large voltage. Typically, the -7, -10 like that. when we apply such a large reverse voltage, there is a high electric field in the depletion region. So this high electric field in the depletion region causes hopping of this charge carriers, and if the electric field is increased to the level of 10 to the power of 6 volts per centimeter by adding reverse bias, so electron participate in the covalent bonds can be turned away. That means there is a breakage of the electron covalent bonds here, and they become the mobile. As you are seeing here, the bonds get broke and they become mobile, and they start moving into the conduction band. And the current, whenever there are electrons in the conduction band, so there is a this becomes electron becomes totally free, and more electrons in the conduction band, that creates a lot of current, okay, under the breakdown, Zener breakdown mechanism here. So this is one type of breakdown, which is Zener breakdown. This is energy band interpretation, of course, okay, as you are seeing here, under reverse bias, okay. So the electron keep hopping from valence band to the conduction band here, okay. Other type of breakdown, which is avalanche breakdown. Avalanche breakdown typically occurs for the lightly doped junction at high reverse bias. Typically, minus 50, minus 60, 70 volts. The for high voltage, reverse voltage. Okay, this avalanche breakdown occurs here. So under this avalanche breakdown, as I told you, when we compare Zener breakdown and avalanche breakdown, avalanche breakdown occurs at higher voltage, compared to Zener. Zener always occurs at earlier. Zener breakdown, if a diode is uh, breaking down at say minus 7, minus 8, that means our interpretation tells us it is Zener breakdown. If a PN junction breaks at say minus 70 or minus 75, we can interpret that as an avalanche breakdown, and we'll give the interpretation even here also, why this how exactly the breakdown occurs due to the avalanche mechanism here. So first condition is avalanche breakdown typically occurs at lightly doped junctions. When the junctions are lightly doped, under that conditions, if the high reverse bias is maintained, so then the avalanche breakdown will result here. The high electric field at the reverse bias junction causes impact ionizations. Okay, so in the previous Zener breakdown we have seen the tunneling effect, but here we are seeing the impact ionization effect here. So due to the impact ionization under reverse bias, this causes the high electric field, and let us see high electric field what it results here. An electron hole pairs is created when a high electric field. An electron hole pairs are created when a when a high energy electron collides with it. Okay, we will see that here how exactly the electron hole pairs are created due to the impact ionization, and this process can it keep repeating, and that causes a multiplication of the carriers. Okay, as you can see here, let me go here. Let us see these two types of interpretation, and now we have cleared with with this 3 point. The first point tells you that avalanche breakdown occurs at lightly doped and high reverse bias, and because of high reverse bias, that causes high electric field. The high electric field causes the impact ionization. Impact ionization causes more electron hole pairs. These electron hole pairs is because of the break in the covalent bonds, and this more and more bonds are broken here, and it causes the multiplication of the charge carriers. So this is shown here in the energy band diagram interpretation, as you can see here. So here in the reverse bias condition, you can see here the electrons which are present here, minority carriers here. So here the electron tend to travel into the you can see that lower energy levels. Okay, electrons try to occupy the lower energy levels, and you can see that electron try to rupture the bands here. So this the covalent bonds which are present in the here, those bonds are ruptured, and the more and more electrons are becoming free. As you can see here, arrow mark here, the electrons break the bonds and that becomes free, and this in turn break other bonds, and that also becomes free here. So okay, this is an energy band interpretation here. Okay, and if you look at the physical interpretation of this, you can see here this is an electron which is a minority carrier on the p side. This is neutral p region. This electron will, because of high electric field, this may smash into this covalent bond, and this covalent bond breaks, and makes releases electron from this bond, and there are two electrons you can see here and one hole has been released here. Okay, so this due to the electron colliding with this covalent bond here. Like this, the multiple collision will happen. So these electrons which are internal free, that may collide with other covalent bonds, and it may set the electrons and holes as a free here. This is what you are seeing here. See, first electron collides with this and it made this two electron free, and this again hole has set free, and this hole will collide with another covalent bond here, and this has set another two holes as free, and electron as free, and this electron colliding with other covalent bonds here. And you can see this process is the repetitive, it's a cumulative process, and more electrons and holes are set free by this mechanism here, and hence the breakdown will occurs. Okay, so at high reverse voltage here. So this is physical interpretation here. Okay, this is also called as avalanche multiplication here. Avalanche multiplication means one electron colliding with the covalent bond and releasing more electrons and holes here, and holes again in turn collide with other covalent bonds and releases electrons and holes here. This process becomes cumulative, and then we may reach circumstance such that more and more electrons and holes are released from the covalent bonds here. So this is called as a physical interpretation, and when more electrons and holes are released here, this conducts this heavy current will flow in a device, and that breaks the p-n junction here. Okay, so this is called avalanche breakdown. And lastly, we have here this is a graph of shows between breakdown voltage and the doping density. X axis is doping here. As you can see, at 10 to the power of 15, 16, this is doping keeps increasing as you move away from the y axis. This is x axis shows you the breakdown voltage here. And we have shown for different materials here. First one is we start with germanium, because germanium has got lower band gap. And as you move higher, you can see that there is silicon which has got 1.1 electron volt band gap, gallium arsenide, gallium phosphide, which are again higher band gap energies here. What this graph shows you here is if you do more the doping here, the breakdown voltage keeps decreases here. Okay, so for example, you can see here for the 10 to the power of 16 here, so the breakdown voltage is less compared to the doping of 10 to the power of 15 per centimeter cube here. Okay, so more doping, the breakdown voltage keeps decreasing here. And also you can see that the band gap also, you can see if you have a more band gap here compared to, see, germanium has got very less band gap here, and silicon has got very more band gap here, and that increases the breakdown voltage here. Okay, that's with that I think we have completed this the breakdown mechanisms. Next class we will take up this the approximation of the p-n junctions with ideal diode piecewise approximation. So this will take up in the next class here. Okay, different approximations of the p-n junction is. So diode, basically if you look at characteristics, it behaves in a nonlinear manner, but this can be interpreted in different ways, like ideal diode, ideal diode with offset voltage, ideal diode with offset voltage and resistance. These interpretations are called as the diode approximations, piecewise linear approximations. We will see the significance of these approximations with reference to the application. Okay, so with that I think we'll wrap up today's class, and if you have any doubt I can take this session for doubt.